Okay, all good?
Yep.
Okay, thank you so much. And thanks to everybody in the audience for coming and joining and spending a whole hour of your time thinking not just about shielding in a broad sense, but specifically, how do we compare different shields and figure out which ones are the best for our applications, different ways of characterizing that. As Lucy mentioned, I'm currently president and chief engineer of EMC United, but throughout my career, I've had the opportunity to work on a number of different kind of projects and platforms. And so that includes things where you house everything in metal and you shield every single cable and you never use chassis for current return. So that'd be most of my NASA projects. Then there are times where you house everything in metal, but then you bolt it to a composite chassis, and then you try and shield some of the cables, but not others. That would be the work that I did on the Dream Chaser spacecraft. Of course, in automotive, for the low voltage side, you house everything in plastic, use chassis for current return. You try to avoid shielding anything if you can help it. So those kind of experiences inform the presentation I'm going to give today. But honestly, more importantly, is the work that I've been doing as a member of the working group for a new IEEE standard that's being drafted. And I'll talk a little bit more about the details of that. But it's through going through these different industries and seeing how different industries tackle similar problems. It's all the same physics, but they use different standards to address their different needs. I became a diehard standards geek, and that landed me in the position now of Vice President of Standards for the IEEE EMC Society. So that also sort of will inform the presentation. So getting to shielding, I think we all want to believe that shielding is kind of that knight in shining armor that's going to save us from, any regulatory failure. And it would be wonderful if that were true. But, even for medieval knights, there was, shielding that was better and shielding that was worse. So some ways that you might evaluate a suit of armor could include, puncture force versus slicing force. What materials are it made out of? How heavy is it? Obviously, is going to be a key consideration. The flexibility, can the knight, the warrior, actually move in that armor? How much does it cost? And I mean, looking at that picture on the right, you can tell the aesthetics did play a part, right? Sometimes you just want functional, and sometimes you want it to be functional and gorgeous. Probably cost played a little bit less of a role for whoever made that. Now, in the realm of the less perhaps beautiful and less historic, when we're looking at the shielding of either our electronics modules or our cable bundles or coaxial, instead of evaluating, for instance, puncture and slice force, we do need to know how well does it stand up to shock and vibe, especially for the aerospace industry. If it's going to fall apart, if it's perfectly good EMC shielding, but it's going to fall apart when you're actually stacked on the launch vehicle, it's not going to be very useful. But we still care about materials. We still care about weight. To an extent, we do care about flexibility, right? For cables, we care about that bend radius, whether we can route it all the places that we need to. And even for a box enclosure, we need to determine if, for instance, it's going to be a replaceable unit, or if at some point you might swap cards in something. Is it accessible enough for a user or a technician to interface with while still providing the necessary shielding? Cost obviously is a huge consideration. Aesthetics still play a role, honestly. When you're presenting the options to management, there are things that are going to look better to certain folks than others. It's silly, but it's there. But another thing that we add that the medieval knights did not have to worry about was transfer impedance and shielding effectiveness. And those are two of the key things that I'm going to talk about today. I would hate to get through a presentation without bringing up this particular slide at least once. This is what I call the fire triangle of EMC. And even though my fire triangle looks like an oval, it still has 3 parts. So I call it the fire triangle because a lot of us learned as kids that to have a fire, you need 3 things. And those things are fuel and a heat source and oxygen. If you take away any one of those things, you've put out your fire. So if you smother it with a blanket, you're essentially taking away the oxygen and putting it out. If you pour water on it, you're really removing the heat and putting it out. Well, similarly, to have an EMC problem, you need three things. And those things are a noisy source, a sensitive victim, and some coupling path between them. And that can either be sort of through the air radiation, or it can be conducted emissions and susceptibility through shared electrical wiring. When we're talking about shielding, we are really focused on breaking up that radiated coupling path. Just adding shielding is not actually doing anything to make the source less noisy or make the victim less sensitive, although, I mean, depending on sort of how you look at it. But we're really trying to interrupt that radiated coupling path to take all that noise and, keep it away from our sensitive electronics, or keep it away from the regulatory antenna if you're trying to add shielding to pass, for instance, radiated emissions requirements. It's not going to do anything to solve a conducted emissions or immunity problem. So just to keep that in mind, shielding does some things, but it doesn't solve every problem. So as I mentioned, I'm part of the working group for IEEE P2855. So that P number means that it's a project, which means it has not yet been fully voted on and approved and published. So that basically means that it's in the draft stage. The mouthful of a title for this is Recommended Practices for the Electromagnetic Screening Effectiveness Characterization of Cable and Connector Assemblies in the Frequency Range of DC to 40 gigahertz. That committee has bitten off a lot. They were first approved to move forward in 2019. We think we're going to get it out by 2026. The standards process does not move quickly. But in the course of this, we've been bringing together a lot of different test methods and different approaches to try and put in one place these different techniques that are good for different purposes so that people can really compare apples to apples. And that's going to be sort of a theme as I talk through some of these different methods, not just for cables, but also for enclosures and board level shielding. There are also a couple IEEE standards that are relatively new that I'll mention that have similar approaches, but for, again, enclosures or for board level shields. Some other shielding standards that you might run into, I'll be drawing on IEC 62153, and also 299, 2715, 2716. We'll talk about all these in a little more detail. But just so you know, one of the original drafts of IEEE P2855, the one that we're working on now, had 442 references for cable-related standards. Now, those were not all EMC based, right? They were materials, waterproofing, aging, abrasion resistance, bend radius. It was, anything to do with cables. But it's funny when you think of something that seems so simple, just how complex it can get. And that page after page after page of references really reminded me of how complicated just cabling can be, getting electricity from point A to point B. So what are the things we can measure? And we call these measurands. That's the official term for the things we can measure. And these are all the different things that we have listed in P2855. But I'm only going to focus on a few of them today. So DC resistance, shielding effectiveness, and transfer impedance. DC resistance, because it's super simple. We can cover that in no time. Shielding effectiveness and transfer impedance, especially because in the States, you're going to see these more often than almost any other measurands. And the difference between them, I think, is sometimes not as well understood and is very important. The other thing is that, for instance, magnetic attenuation, that's for a longer seminar, and I'll be giving a longer seminar on November 5th if anyone's interested. We'll talk a little bit about magnetic shielding in that case. And that last one on the list, electric and magnetic polarizability, we'll at least touch on that. Screening and shielding attenuation and coupling attenuation are closely related to shielding effectiveness. They're more commonly seen if you're working in Europe. And transfer admittance is closely related to transfer impedance. So again, I felt like focusing on shielding effectiveness and transfer impedance would be perhaps the most useful for the audience. So starting out, just looking at cable and connector assemblies. One of the things that I've deeply appreciated about what's coming out of the 2855 working group is we've got a couple charts that look like this. And what this is telling us is there are a whole bunch of different test methods, and each one has its own bar line on the chart. The x-axis is telling you in what frequency range would you expect this test method to be most useful. And especially for triaxial cavity and localized injection, we'll talk about sort of why they stop where they do. But it does tell you, if you're concerned for some reason about very high frequencies, your options for testing that are definitely a little bit more constrained. Another one is, again, just very, very practical, where the y-axis is the size of your connector assembly, essentially. So, it's one thing if you are testing a coaxial cable with an SMA connector, one of the very, very little tiny ones for relatively high frequency coax, you can fit that on anything. As long as you've got the right, length, any test fixture is going to be able to accommodate that. But if you remember, up at some of the slides up at the top, where you had this huge bundle of avionics cables, which I believe came from an Airbus airplane. It had dozens of conductors in it. Some of them were twisted shielded pair. It had overbraid over the entire thing. That's a monster to test. And you're going to have a big problem trying to fit that in a triaxial cavity test fixture. And I've got a picture of that a little later on. If you have something that large, testing in an anechoic chamber or a reverb chamber is probably going to be your best bet. And of course, that gray column sort of all the way at the left there, DC resistance, you can test that anywhere and you can test it on anything. So that one's nice and simple. The other thing that we've done is break down the construction of a cable into different zones, right? Because sometimes you're going to be including your connector up to a certain point. And we wanted to be able to sort of define for a given test method, how much of the cable are you actually including? So for instance, you can almost think of a zone 0 out here, which is the actual box that something is mounted to. Now, generally speaking, if you are the person controlling the cable, you do not control the box. So you don't necessarily want the box to be part of what you test. But you should be able to control, mostly, generally speaking, the plug, the back shell. Zone 4 is where the shield gets terminated. So where it goes from being a continuous shield to being something that interfaces with the connector back shell. And then zone 5 is that long continuous run, that when you're thinking of a shielded cable, you're generally thinking of that long continuous run, even though from an EMC point of view, all the important bits happen at the ends. Now, not every cable is going to have every zone. Some of them, the construction might be so simple that zone 2 and 3 are essentially the same or kind of merged together. This cable here, where you've got a shield that's not connected on either side, it doesn't have a zone 4. Whereas this one, where you've got an EMC sock in place, at least that's how I've seen it referred to in aerospace, where it's only meant to be connected and protecting one side for whatever reason, that only has zone 4 on one side. So this is a helpful way to think about what's included in the testing that you're doing. So again, with the different test methods or test, in this case, test measurands, that's going to be applicable to either in the broadest sense, zone 1 to 5. So that includes the connector and how everything fits together, Or you can see here that the transfer parameters, so that's transfer impedance or transfer admittance, which are often calculated as a per unit length value. That is going to be only looking at the, the tubular material that's running the length of the cable, and it's only looking at that material. It is not looking at how it's installed or how it's terminated. So that's one of the things that I really want to make sure people understand, is that when you're looking at something that says, our transfer impedance is X, that does not fully encompass how it will behave when you install it, because what you do to it when you install it could make it a better or worse shield. Specifically, it could make it worse than what was measured when a manufacturer of shielding material was measuring transfer impedance. So just to start, knock out the really simple one, DC resistance. All that tells you is something connected or not, which is very important to know, right? Like if you're going through and installing a whole bunch of stuff, it's a good sanity check to just remember, did we basically plug everything in correctly? Now, the one thing is, though, it's not going to tell you anything about the method of making that connection. So in this case, you've got this relatively long pigtail that's terminating a shield. So it's bundling all the shield material into one little strand and then clamping it to the back shell of the connector. Whereas over here with the sock, you've got the braid is extended out and then clamped around the back shell with a full 360-degree connection. Those look exactly the same to a DC resistance test. Now, it will tell you, that this one up here isn't open. And, presumably whoever made this cable, that's what they want. But, so DC resistance, it's important, but it's not sort of the end all be all. Now, everything other than DC resistance, pretty much all the test methods I'm going to talk about, and most of the other ones that I'm aware of, when you're looking at the shielding effectiveness per frequency, so that performance over that range of frequencies, you're pretty much looking at making your cable under test into a pseudo coax. So either you are already testing a coax cable, or you are going to take that big bundle and make it into kind of a coax cable. And so what that generally means is taking all those inner conductors and shorting them together so that it acts like one giant conductor on the inside. And then you've got your shielding material on the outside. One of the standards I mentioned earlier, 62153, has really good step-by-step instructions for how to do this kind of preparation. But this allows you to take your measurements with things like a spectrum analyzer or a vector network analyzer. Okay, so looking at shielding effectiveness first, fundamentally, all the shielding effectiveness measurands that we're going to talk about today, they all have the same concept. You're going to measure the field or the energy or the power that's picked up in the unshielded configuration versus the shielded configuration. And the better off, the more reduction you get, the better your shielding effectiveness is. So in this case, if you are measuring based on the power picked up by the inner conductor, you can measure that unshielded and then shielded. And if you measured everything in something like dB milliwatts, then the math is super easy. One of the things I like to say is that EMC engineers, we don't even want to go back to elementary school math. Multiplication and division, oh boy, that's too much for us. We work in decibels, so we can go with kindergarten math. So we only have to add and subtract. Works great. But one thing that you'll notice is that assuming that, assuming you measured everything right, the power picked up unshielded will always be greater than the power picked up in the shielded configuration, which means that shielding effectiveness will always be a positive number where bigger is better. So something that has a shielding effectiveness of 60 dB is going to be objectively better than something that has a shielding effectiveness of 20 dB. So that makes it very intuitive. One of the ways that you can measure this, obviously there are a lot of ways that you can measure this. I just wanted to highlight this one here. For my money, I think it's one of the best ways. It's going to be one of your fastest ways to cover a very large frequency area. Um, so you will find some details. You will find basically a sketch of how to do shielding effectiveness measurements in a reverb chamber in IEC 62153-4-21. It is remarkably shy on details. I was working through it for a particular client of, okay, step by step, how do you actually do this? And man, it requires a whole lot of fill in the blanks. But again, fundamentally, you're going to, have your cable under test fully within the uniform field area of a reverb chamber. The thing that's labeled WC is called a witness cable. And all that's basically doing is it is giving you a coaxial connection from your cable under test all the way back to the chamber wall. So it basically makes the system continuous. Then again, you can measure that the energy picked up by the cable under test when it is shielded and when it is unshielded. You can also, one of the methods that's actually in 421 is to compare the energy picked up by the cable under test with the energy picked up by the reference antenna. I don't love that. I feel like it would overstate the shielding effectiveness. I prefer to compare unshielded versus shielded of the same cable assembly. But again, lots of different ways to skin the cat. The nice thing about reverb chambers is it lets you get through a lot of frequencies very quickly. And also, it's illuminating your target from all the different angles. That doesn't matter quite as much when you're just testing a standalone cable, but for a lot of applications, that simulates the real world illuminations a little bit better than just a fixed orientation. The limitation, of course, with the reverb chamber is honestly on the low end, right? It's only able to establish that uniform field area down to a certain frequency, beyond, a lowest usable frequency, beyond which you're not getting statistically meaningful data. So whereas most of the test methods have a bound on their upper limit, reverb chamber testing usually has a bound on its lower limit of usefulness. And again, like I say, there are a whole bunch of different ways. You can do the same thing in an anechoic chamber. You can use different test methods to get that same measurand. That's just one that I think is useful over a very broad frequency range. Moving now to transfer impedance, you can see this is a completely different equation than shielding effectiveness. Here we are just using Ohm's law, essentially, the AC version of Ohm's law, V equals IZ. Swap it around, you get Z transfer impedance equals voltage over current. And what that is the transfer impedance is equal to the voltage induced on the inner conductor divided by the current on the shield. And basically, what that's going to say is that, in an unshielded case, obviously, pretty much all the voltage gets developed. Whereas in a shielded case, you've got shield flowing on the current, current flowing on the shield. And if your shield is better or worse, you will get more or less voltage developed on the interior conductor. Now, a couple things about this is that you'll note that for this equation, smaller is better. So for a given current, to have less voltage developed on the inner conductor, you want a smaller transfer impedance. So for instance, if you have a shield that's made up of a composite material where some of it is very conductive, like tin-plated copper or what have you, nickel-plated copper, and some of it is made of something that's a little less resistive, that's going to tend to give you a higher transfer impedance. And so you might get a little more voltage developing on that inner conductor than if you had a fully conductive material. Also, anything that has that braid, that has that weave, is going to probably be slightly less, slightly higher transfer impedance will be slightly less effective than, for instance, a solid conduit. Now, it's rare that you actually get to use a solid conduit, right? But It's that same concept. Now, again, transfer impedance is only looking at that material, braided versus solid, or, braid with 85% optical coverage versus braid with 65% optical coverage, or, again, different materials. It is not telling you anything about how the terminations affect the overall performance. The other thing that I wanted to mention before I move off this slide, very early in my career when I was first getting into EMC, transfer impedance was described to me as the inverse of shielding effectiveness. Now, I can see what they were thinking, because shielding effectiveness, bigger is better, and transfer impedance, smaller is better. But they are very different equations. You derive them very differently, and uh, they are not, that you can't just directly relate them to each other. The test methods are different, and everything else. So again, to make sure that people understand that these are very separate values. Now, to be fair, if you have good shielding effectiveness, you probably also have a nice low transfer impedance, but that's not necessarily true. Again, because transfer impedance is looking at the material, where shielding effectiveness is taking into account those terminations, you can see that there's a huge difference there. Probably the gold standard of testing transfer impedance is when you can use a triaxial cell. And the main description of this test method is that 62153 standard -4-3. That's one of those IEC standards that has a million different subparts. What you're going to do with a triaxial cell, and actually let me skip ahead and show you a picture of what this ends up looking like. You're going to have your cable under test completely encased in a solid metal hollow cylinder. That's going to be terminated at different ends so that you can pull, you can generate a signal and then pull your measurement out from both ends. And in this case, this is from some of my colleagues back at Electromagnetic Applications. They were feeding and measuring this using a network analyzer. The things that that really lets you do is you get a current flow that's induced between the cell, the interior of the cell, and then your shield. And then you're going to measure that voltage that develops on the interior conductor between the shield and the, you're going to measure the voltage that develops on the interior conductor. The thing is, because that is a completely self-contained system, it is basically immune to any electromagnetic noise bouncing around in the environment. So you can set that up on just any old bench anywhere. You don't have to reserve a shield room or an anechoic chamber to do it. That cylindrical fixture also allows you to say that when you're inducing a current on the shield, it is going to be evenly distributed across the entire circumference of the shield. And we'll see in another test method where that's less true. So this leads to very repeatable measurements. But for instance, there's no allowance for different kinds of shield terminations. You're terminating into solid RF connectors no matter what, which is why, this is really only measuring that zone 5, straight material. So we saw this picture. Now, one thing that I wanted to highlight here, so this is a similar diagram just from a different document. Take a look at this. L is much less than wavelength constraint. So this is something that's, not that we don't have time to get into today, but hopefully that I'll be able to cover in my more extensive shielding seminar in a couple weeks. These measurements can be very sensitive to cable resonant effects when the length of the sample starts to approach the length of the wavelength of the frequency that you're interested in. That's really what sets the upper bound on the triaxial cavity and localized injection methods, and I'm going to be talking about localized injection next. The IEC standard recommends not going above 30 megahertz for a 1 meter sample, maybe 100 megahertz for a 30 centimeter sample. So, 2855 recommends only using it up to 10 megahertz. That's a fairly significant limit on the test method, especially since cabling can be part of a radiated emissions or radiated immunity problem, into the 200 megahertz pretty easily. So while triaxial is, very, very controlled, and from a theoretical standpoint, it is, like I say, basically the gold standard, it does have that length limitation. Now, sharing the length limitation, but being a little more flexible and easy to do, is localized line injection. And this is coming straight out of the draft of 2855. My colleague, Charles Julian, who's a senior EMC engineer, in fact, I think he just got bumped up to fellow for Safran, which is a big supplier for Airbus. He's developing this method. In this, you're going to take your cable under test, and instead of having it fully enclosed in a triaxial fixture, you're just going to have it mounted to brackets over a ground plane. Then you're going to inject current using a straight up bulk current injection probe. You're going to monitor what that current is using a separate injection probe. And then you're going to measure the voltage that develops on the inside. So it's the exact same math. It's a much easier setup because you don't have that entire, enclosed brass tube, which is quite unwieldy. And if you're, you can't just easily swap a connector on those things. They're very specialized. But here, it's relatively easy to take those brackets and just move them apart, move them together if you've got different cable sizes. The downside is that because you're routed in free space over ground plane, as you're injecting the current, it is going to tend to concentrate on the bottom of the cable shield because that is closest to its return path on the ground plane. So it is not going to evenly distribute itself around the perimeter of the shield. Now, does that matter? It depends on how sensitive you are to these measurements. In my world, plus or minus 6 dB, I'm good. It tells me if it's a good shield or a bad shield. It tells me the difference between 6 dB of shielding and 20 dB of shielding. So, from my mind, I'm a little less sensitive about that. But if you have, significant signal integrity concerns, for instance, or, you're trying to validate certain models, this might be a deal killer for you. But like I say, I like it because it's relatively easy to set up. It's very intuitive to understand. So talking for a moment now about enclosures, so leaving cables behind for the moment, what can I measure for enclosures? Well, you can generally measure the same things, and we're going to focus on DC resistance and shielding effectiveness for the same reasons, except you can't measure transfer impedance or transfer admittance on an enclosure. And that's because those particular measurements are very based on the assumption that you have a standard interior conductor that you can always measure, that basically will always have the same relationship to its shield, right? It's going to be relatively centered in a shield, and it's going to be separated from that shield by some kind of insulation. It's going to be long and tubular. So that's something that they can count on. You can put anything in an enclosure. There's never going to be that kind of standard interior thing that you can measure. So transfer impedance, transfer admittance does not apply to enclosures. Now for DC resistance, again, fundamentally, you're just asking yourself, is it electrically connected or not? Now, how well is it electrically connected is more of a question that you can answer with enclosures, and sometimes it matters a little bit more. Again, if all you care about is, did it close or not, your kind of fluke digital multimeter, that's going to do the trick for you. If you were working on a NASA project and you've been told that you have to meet Class R bonding as per NASA standard 4003, it's going to tell you that you have to measure 2.5 milliohms, no more than, over any particular joint. So for instance, where the shield meets the back shell, 2.5 milliohms. Where the back shell meets the rest of the connector, 2.5 milliohms. Connector meets the box, 2.5 milliohms. You need more specialized equipment for that. Generally speaking, you need a 4-wire milliohm meter for that. You can get them. They're, not as common and they're not as cheap. But boy, if you want to know exactly how good your electrical bonding is at a DC level, that's what you're going to need. Now, I just want to make a little pitch that no one should die on the hill that is 2.5 milliohms. It is a number that comes from, it actually originally comes from lightning, not from RF control. And it goes back to the 50s. And it tells you absolutely nothing about how something is going to perform in the presence of high frequency noise, technically. Now, it's one of those numbers that we've kept around because it's useful, because if you have good metal-to-metal connections, you most likely can meet 2.5 milliohms, and you will most likely also have good RF performance. But man, trying to throw all your effort into meeting 2.5 when you're reading 8, that might not be the best use of time and effort. So that's just my pitch on class R bonding. Okay, but once we get into enclosures and shielding effectiveness, again, all this is the same concept that we had back in cables. How much power does something pick up when it is shielded versus when it is in free space? So actually, the most popular, the most used IEEE standard that is sponsored by the EMC Society is IEEE 299. And that is methods for measuring the shielding effectiveness of person-sized or room-sized enclosures. And it does the same math, except, in this case, it's doing it in linear units instead of decibel units. Comes out to exactly the same thing. Your shielding effectiveness in dB is your 10 log 10 of power without the power that's picked up in free space, so with no shielding, versus power that's picked up when the shield is in place. Exact same concept, very intuitive, and bigger is better. Now, one thing that 299 also points out is that instead of just doing power, you can measure field strength, you can measure magnetic field strength. There are different things that you can measure, and it's the same ratio relationship. But they recommend that above 300 megahertz that you focus on the power measurement, just because you're talking about the power. It's more straightforward to talk about the power received by your receive antenna versus your transmit antenna. And by the way, there is also an IEEE 299.1 that is for small enclosures, box-sized enclosures. It is a bit of a mess because trying to get an antenna into a small enclosure and take into account the coupling between the antenna and the shield walls, because you can't get it very far away from the shield walls, that becomes a lot more challenging. Both 299 and 299.1 are currently in the process of being revised. We are just getting started on that process. We'll be standing up the working groups by the end of this year and really starting work early in 2025. If this is something anyone feels very passionate about, let me know, and we can talk about potentially getting more people involved in the working group. So now is the time if that is something you are interested in. Now, talking about planar materials. So now you're not talking about a full box, you're just talking about the material itself. And this is kind of equivalent to that, when you're looking at transfer impedance and you are only looking at the shield material. There's a couple different ways to do this. There's an ASTM standard that actually fixes the planar material sample in a coaxial fixture and then calculates shielding effectiveness based on the change in insertion loss. Again, that's a little less intuitive for people who are not, in the RF world all day, every day. But it's self-contained. It makes very good sense. It also, of course, has some frequency limitations. Then another way of characterizing it, IEEE 2715 is a relatively new standard. It's using the method of 299, but just to evaluate a coupon sample of material as opposed to an entire enclosure. And again, you're going to mount your sample in some sort of chamber arrangement, and then you're going to take your measurement with the sample in place and with the sample dismounted you make that comparison, you get your shielding effectiveness number. I really wanted to highlight this kind of chart, and I've got one more like it at the end. So the group that developed IEEE 2715 did a whole ton of research, and they did a whole ton of round robin testing where they took, certain constructed samples, sent them around to a lot of different labs, and had them measure the shielding effectiveness with a lot of different methods. And they published the results. Now, it is easy to look at this and say that this is a nightmare. The fact that, for instance, VIRC is the green line, that stands for basically vibrating reverb chamber. So that's where you make a reverb chamber, but use flexible conductive fabric walls instead of a solid planar enclosure. And then you get your mode stirring effect by shaking the walls. The fact that it is like 40 dB off at low frequency levels looks horrible. But for one thing, wide variations in EMC testing at low frequencies is nothing new. Pretty much every EMC test struggles with repeatability at low frequencies. You can see you get a lot better agreement as you get to higher frequencies. So that's something to certainly keep in mind, again, when you're looking at these different methods. It also really highlights that when someone gives you a shielding effectiveness number, and this is as true for cables as it is for enclosures or planar materials, you need to understand how they got that number. So just taking a shielding effectiveness number from, say, one vendor and comparing it to a shielding effectiveness number from a different vendor, you may not be comparing apples and apples. If they tested it with different methods, you may run into these kind of discrepancies where one looks better, but it wouldn't actually perform better in your installation. Now, if you control the testing, then, if you can sort of arrive at one method or two methods that cover, the situations that you are going to have and the frequency ranges that you are interested in, and then you keep that test method consistent from sample to sample, then you know exactly what you're getting. It's a very similar story for board level shields. Again, relatively new IEEE standard 2716 for evaluating the shielding effectiveness. It's the exact same concept. You're going to mount a small little microstrip antenna on a board. You're going to put, a board level can or shield over that microstrip, and you're going to measure power picked up with and without the shield in place. Again, the working group for 2716 did that same round robin. In fact, there was a lot of overlap in membership between the two working groups, and they published their results. And again, it kind of looks like an unholy mess. Within this plot, you've got variations, easily, 20 to 40 dB. Kind of similar story with this plot over here with the perforated shield. But one thing I would like to highlight before you just throw in the towel and say all this testing is useless, if you look at the same method from chart to chart, your intuition tells you that the solid shield is going to perform better than the perforated shield. And if you look at the blue, it's higher on the solid shield. If you look at the red, it is higher on the solid shield. Generally speaking, the green also higher on the solid shield. So if you compare two shields that were measured with the same method, that will likely tell you one is better or worse than the other. However, if you, again, are getting samples from different vendors and they each do their tests a slightly different way, it's much harder to compare those numbers in a meaningful way. So with that cautionary tale, that brings me to the end of the formal presentation. And I think at this point I can open it up to questions, although I believe Lucy might have one thing while people are getting their questions in.
Yes, let's do a very quick poll. Yeah, there you go. You should see it on your screen. Oh, and I will send you the recording and the slides this afternoon.
Wonderful, thank you. I did see a question popped up probably during the discussion on triaxial cell testing. The cable length has to match the length of the fixture. Basically, you either build the fixture to match the cable length, or you change the sample length to match your fixturing. But it has to be, the cable under test has to go all the way end to end on the interior of the triaxial fixture. That's one of the reasons why, like I say, that localized line injection method is so much more flexible, because once you've built a triaxial fixture, you're kind of locked into a lot of choices at that point in terms of connectors and in terms of cable lengths.
Okay, if we have any other questions, you can post in the Q&A section, or if you want to unmute yourself, just raise your hand. You have the option in Zoom to raise your hand, and I can unmute you. Oh, we have another one.
Can I comment on the choice of material for box on PCB shielding? That's not something that I tend to have to worry about too much. From an EMC perspective, as long as it's conductive, as long as it's doing the job, whether it's copper or aluminum doesn't make that much difference to me. That's going to make a lot more difference to, the people who are watching the BOM cost, the people who are watching, weight and flexibility and material compatibility and more mechanical considerations. So that's not something that I tend to have a lot of input onto. The shield shown in zone 5, what's the point with no connection to a bonding point? Man, that is a great question. Now, I know for that diagram, they are just illustrating that not every cable has to have zone 4. So, the illustrative purpose of the diagram is for that purpose. However, you do still see people who throw shields on things without connecting them, and it doesn't do any good whatsoever. Let's see. Marty says, so you can't find or meter and then extend the length. If you are doing triaxial fixturing, that's true. Like I say, you're completely locked in. Let's see, question, what is the best way to measure DC to low frequency current flowing in a shield? For testing applications in real world settings, an example would be an emitter, like an AC servo cable assembly enclosed in a shield. Man, that is, you're absolutely right. That is a tricky problem. Because, and basically, for folks who are less familiar, your RF current probes that you can clamp around or put around a cable and measure the current flowing on the cable, those tend to be in the kilohertz and up range. And in fact, getting something that goes down to 10 kilohertz is like, woohoo! And then the kind of, I don't know if you've seen the yellow and red clamp on, they look a little bit like lobster claws that you can get from a local hardware store. That's really only meant to measure 50 and 60 hertz, or maybe up to 400 hertz, depending on, how fancy it is and what system it's meant to be measuring. Covering that gap between the low frequency and the quote unquote high frequency, where you're getting into RF, that can be tricky. Like I said, you could do it with some special fixturing. You could, there might be some RF current probes that go down that far. That's definitely a more, there's not a simple, straightforward answer to that I know of.
We have someone named Don Masters. You can unmute yourself and you can ask your question. Okay, well, in the meantime, you have another question in the Q&A.
Okay, when are you needing shielding in which, I think the question is probably, how can you tell in which frequencies you really need shielding? So that is a great question, and it very much depends on what you're shielding from and what you're shielding against. Well, right, the thing you are shielding, the victim, and the thing you're shielding against, which is the threat. So, for instance, generally speaking, like people don't worry a ton about shielding against automotive radar. So automotive radar, it's kind of high power. It's definitely directional. It's 66 to 77 gigahertz. Cables just aren't good at responding to that level of, or that frequency of power. It goes like with those short little wavelengths, it just dies out before it really has an effect on anything that a cable's connected to. So, in rule of thumb, your cable shielding becomes much less important at high frequencies for those kind of radiated immunity and radiated emissions problems. How much shielding do you need? Again, that really depends. So when I worked at Ford Motor Company, we were able to get away without shielding our CAN lines even on electric vehicles, because the high voltage architecture, that can have really significant threats at those frequencies where a meter or two of cable can cause huge problems. But because we had enough control over the high voltage architecture and went for very high quality stuff, CAN lines, no problem. Just twist them and go, and we didn't need to add shielding. When I've done troubleshooting consulting for other companies, the interference from the high voltage system to the CAN lines was often like enough to completely put a vehicle out of commission. They did need to add shielding. So, again, it depends. It's the EMC answer of choice, right? It depends. But if you think of that EMC fire triangle of, again, what the threat is and what the victim is, that will tend to tell you where you need to focus your shielding efforts. And then if there are emissions in the hundreds of megahertz, does the thickness of the shield matter? Is thicker better at those frequencies? For me, thickness almost never matters. By the time you're up into the RF frequencies, the skin depth is so low that none of the high frequency current is actually using the entire cross section of the shield. It's generally speaking staying on the outside. Now, there's some subtlety with that in terms of overbraid, because you have the weave that's taking individual conductors inside and outside. There's a little more nuance there. But again, mostly at high frequencies and certainly in the hundreds of megahertz, aluminum foil is as good as 1/4-inch pipe. Somebody's like, oh, interesting results with CAN. Always had, yeah, and again, a lot of places do have to shield CAN. The more I learn, the more impressed I am that Ford was almost always able to use unshielded CAN lines. Hey, Jared, how's it going? Good to hear from you. Jared and I used to work together at EMA, so let's see. IEEE is an international organization. Some standards can be hard to implement on a global scale. Yes, so global standards are very tricky. They're tricky to negotiate. It's actually really interesting. This is me being a standards geek, right? It's really interesting how different organizations work. So IEEE, even though it's global, it is completely done by members. So individual members usually vote, or for some standards, not EMC ones, you'll vote by entity. So Boeing will have a vote, or HP would have a vote, or whatever. Now, for CISPR and ISO, they're global standards and they're voted on by country. So America gets one vote, Norway gets one vote, Saudi Arabia gets one vote. The politicking that goes on when you are voting by country dwarfs any politics that I have to deal with when it's IEEE members voting as individuals. Now, and that's one of the reasons why, like, ANSI standards, so that's American National Standards Institute, had some disagreement between CISPR standards, which are one of the international ones. And IEEE is kind of off, kind of doing its own thing. But we, for instance, leave automotive standards to the SAE folks and CISPR and ISO. Man, there's a lot that goes on there. So the other thing is adoption. So countries are more likely to adopt those international standards as part of their own regulatory framework. You don't find IEEE standards as part of government regulations as often as you find it from CISPR or ISO. And it's so you only force people to do EMC right when it's part of a legal regulation, and they have to do it right, or else, you know, there are actual like monetary penalties or, you know, other very negative consequences. The IEEE standards are much more voluntary, and so it's more like, hey guys, wouldn't it be great if everybody did it this way? Look. So yeah, it's a weird world out there.
Okay, do we have more questions? No? Okay.
Again, I'd like to thank Lucy and Sierra Circuit so much for the invitation to speak to you. I'd like to thank all of you for spending some time with me today, and I hope I'll see some of you on November 5th for the extended version, the director's cut, the all-day version.
Yeah, thank you so much, Karen, for doing this webinar with us. And I will send everyone a link to Karen's seminar today, this afternoon. Okay, thank you, everyone. Have a great day. Bye-bye.
Thanks
Thank you,
very much.
Karen.